Good morning. I'm Nadia Dugan, product marketer with Lakeshore Cryotronics, and I'm excited to talk to you today about lock-in amplifiers. A quick background on myself. I have my master's in electrical engineering. I've been with Lakeshore for about 10 years. I started as an intern, worked on our instrumentation, then our sensors, and now I'm a product marketer and I get to talk about our products. So, if you're watching, I'm assuming that you're either trying to learn some of the fundamentals of how a lock-in amplifier works, or you've already started that process of trying to figure out what's the right lock-in amplifier for your application, and you're looking for a resource to help you with that. And I'm here to help you with that. We're going to talk about who are the main lock-in players in the industry. I'll briefly go through how a lock-in amplifier works. Then we're going to go through noise. I'll have a brief noise analysis. We'll touch on capacitance, crosstalk, talk about accuracy. So let's get started then. Now, what's the main purpose of a lock-in amplifier? The main purpose of a lock-in is to extract a signal out of a noisy environment. So if you have a signal that's in the microvolt or nanovolt range, you'll likely need a lock-in amplifier to be able to measure that signal. At such a low level you're trying to measure, you're likely going to have noise dominating that. Another purpose of a lock-in is to remove DC offsets. If you have large DC offsets or large offsets from your sample, maybe it's really prone to self-heating, a lock-in would be really beneficial to your setup. A lock-in is actually really good at removing DC offsets because it uses signal reversal, and it does this by using a sine wave. Now, I'm sure you're familiar with current reversal, where you switch the polarity of the current, and that's a square wave, and this also removes offsets. But at each transition point of when you change the polarity, you have to have the correct blinking time, do the right averaging, and if you don't do this, you're going to have errors in your measurement. The measurement's going to take longer overall. And so a lock-in, because it uses a sine wave, is a lot more efficient method at removing offsets. Then finally, if your signal to noise ratio or SNR, you're looking to improve it by more than 1 to 1 or by 20 dB or more, a lock-in amplifier would be good for your setup. And I'll start going over now what are the available lock-ins in the industry. Before I dive into that, I do want to give an introduction to one of Lakeshore's own instruments, the M81 Synchronous Source Measure System. It is quite a unique instrument, and so I think it needs a bit of an introduction. It's able to take lock-in measurements, but it also does a lot more than just that. And so I'm going to get my camera here and let's go take a look at it. This is our M81 Synchronous Source Measure System, and it can do AC, DC, source measuring, lock-in measurements. It can really do a lot. And the idea behind this was you have these large traditional instrument racks with a bunch of equipment, and bringing that all into one easy to use solution while still keeping to really good specifications. For example, these modules here have really good noise specs. So this is the heart of the system, the M81, and it has the user interface, it does the digital signal processing, and you can connect different modules to it to configure the type of measurement you want to do. You can connect up to 3 source modules, and you can connect up to 3 measure modules. You can see we have a voltage source, a balanced current source, a current measure, and a voltage measure. Both of these measure modules can do a lock-in measurement, and for the reference part of a lock-in, you would use one of these source modules here. And something that's also nice is these modules, right? They're really small, lightweight. They can go right next to your sample, so you can really reduce the cable length between your device to your measurement. And finally, the M81, a really core part of developing this product was making it easy to use, intuitive. And you can see that with the UI here. We can look at different modules here. Let's say, right, this is one of the measure modules, and here's some of the settings. If you had a question over like what's the averaging time, you can click this little info button and it gives a nice description over what that is. So it's just a nice feature, it makes it easy to use. Let me get my camera back up. Great. And my slides. Okay. So the graphic here shows what are the commonly available lock-ins on the market. For the longest time, it's been Stanford Research and Zurich Instruments. As I recently talked about with the M81, Lakeshore recently entered in this space with our M81's lock-in capabilities. The top of this graphic here, I have it labeled by what are the maximum bandwidths of these lock-ins. The signal that you're measuring, you have to make sure that the bandwidth is large enough to measure that signal. So I have 100 kilohertz, 200, 500, and then up in that megahertz range. And you can just kind of see for yourself the different lock-ins here. I'm not going to go through each one. And I also have them grouped then whether they're digital or analog. I think nowadays for most applications, a digital lock-in is probably best suited for what you're looking for. An analog lock-in, it relies on physical components such as resistors, inductors, capacitors, and it relies on these components for like the time constants and roll-off characteristics. So when these physical components change over time because of humidity or temperature changes, you'll get less precise measurements. And it's just not as reliable. And digital lock-ins, there's a whole bunch of digital signal processing, a lot of capabilities that a digital can do and what it can then filter out. Now, an analog does have its place, in my opinion, I'm sure there's varying opinions, for measuring really delicate phenomena. There's actually, which one was it? The SR2124. That was built by popular request because of some people who were measuring super delicate phenomena, and a purely analog unit means that there was no noise going into their sample or what they were measuring. But the downside of having a purely analog unit is that you can't stream data, you can't connect it to your PC, and it's just really difficult to use. So overall, I'm going to lean towards a digital lock-in. And as we continue, I'm just going to focus on digital lock-ins. Okay, so moving on to how does a lock-in work? I'll be brief. I won't go into too much detail here. We have the signal that we're trying to measure, and that's denoted by a sine wave plus our white noise. And the white noise that's uniformly across the spectrum, and that's dominating our signal. And A is the amplitude that we're trying to measure. The reference, that's also denoted by a sine wave, and the reference is typically internal to a lock-in, although a lot of people will also get an external reference. And the reference runs at typically the same frequency as the signal you're trying to measure. So you multiply the signal and the reference. The lock-in does this with a demodulator, and the output is this term here. You get A over 2, the DC component, and then the 2 over F term, the second, which is also called the second harmonic. This is a multiple of that frequency, plus white noise. And all of this goes through a low-pass filter that accounts for the gain, and you get your amplitude. I'm going to touch a bit more on the filtering part. A lock-in uses IIR or FIR or even both filtering. IIR stands for infinite impulse response and FIR for finite impulse response. My tongue catches when I sometimes say the two. And our M81 actually can do both at the same time, and that's a unique feature. So an IIR filter, I have this chart. We have the normalized step response over time, and it gradually approaches the final value, but never fully reaches it. It uses exponential decay, to filter out the noise. And this makes it really good for removing frequencies close to the reference signal, closely spaced interfering signals, and white noise. But the trade-off is it has longer settling times, which means it takes more time to settle to that near final value. On the other hand, an FIR filter, it uses a moving average technique to process the signal. And it's able to go to the exact final value, making it a lot faster than an IIR filter. And FIR filters are specifically good at removing specific frequencies, such as harmonics. And right, since they're faster, they're preferred when you need a faster measurement. I'll touch briefly then on the equivalent noise bandwidth, because we'll need this in our noise analysis. The equivalent noise bandwidth, which is also, you can call it ENBW, it's the width of the bandpass filter centered on the reference frequency. And the ENBW is determined by the time constant and the slope, as shown here for assuming a normal RC type filter. And these are standard equations here with the slope and the ENBW. And yeah, it's just a normal set of equations that you can use for whatever your lock-in measurements or calculations you're doing. You can reference this chart. So let's dive into noise now. This is a very typical noise chart. It's plotting voltage noise density over frequency. And you can see there's two kind of distinct ranges right here. On one side, we have 1 over F noise. This can also be called pink noise or flicker noise. And the 1 over F noise for a lock-in, it's typically spec'd in a 0.1 to 10 hertz range. It's just an industry standard. But you have to keep in mind is that this 1 over F noise region, it still extends past 10 hertz. So you can see here on this chart, right, if this is 10 hertz here, you're still in this range, kind of past that 10 hertz line. And then you go into broadband noise. Broadband noise is also called white noise. It's uniform across the frequency spectrum, and it includes shot noise, Johnson noise, which is also called thermal noise. And these two regions, it's important because looking at this chart, you might think, okay, I should always run at a higher frequency then. But we're going to go through some calculations, and I'm going to show you why you might actually want to run at a lower frequency, even if that means higher noise. I'm going to go through an example noise calculation now using our M81, and I'll start off with doing it at a frequency of 1 kilohertz. We have our voltage measure module and our voltage source module, and these are the specs here. We have 4.1 nanovolts per square root hertz for the measure, and for the source, we have 40 nanovolts per square root hertz. Now remember the source, that's the reference, and we could be using the current source module here, but I wanted to use a voltage source module because the other lock-ins that we're going to compare to, they have an internal voltage source, and then you can see how the calculation goes with a voltage source. We're also converting this into a type of current source almost, with putting a 1 mega ohm shunt resistor. This is very typical configuration people will do when they don't want to get a external current source. But keep in mind that it's not a true current source. The current will fluctuate and you don't actually know what the current is going through unless you had a second lock-in to measure that current. Then we have our filter. Our ENBW will do 24 dB, time constant of 0.3 seconds. That gives us 0.26 hertz. And we have to account for Johnson noise, which is the equation here is the square root of 4K, where K is the Boltzmann constant. RT will do temperature of 300 K and a sample resistance of 500 ohms. So to calculate noise, you take the square root of the sum of squares of all of your noise components. All of the noise components are your voltage measure noise, your voltage source noise, and your Johnson noise. And Oftentimes, when people think about noise, they just look at the voltage measure noise spec, but you really need to consider all three um, noise contributions here. So we have our 4.1 here. We don't need to do anything with that, but our 40 nanovolts per square root hertz, because we have this 1 mega ohm shunt resistor, we need to divide by that, and that gives us 40 femtoamps over square root hertz. Now we want to convert this back into voltage, so we're going to multiply by the sample resistance, 500 ohms, and that gives us 20 picovolts per square root hertz. Our Johnson noise is 2.8, and now we can do our noise. Our noise is equal to the square root over 2.8 nanovolts per square root hertz squared plus 4.1 nanovolts per square root hertz squared plus the 20 picovolts per square root hertz squared. And we're going to then multiply by the square root of the ENBW. And this will then give us an output in terms of RMS. It's hard to conceptualize what the voltage density is in your experiment, that value, but in terms of RMS, that's a lot kind of easier to conceptualize. And that comes out to be 2.6 nanovolts RMS. The graphic here is showing the same noise calculation we did using the M81 1 kilohertz, but now over varying resistances. So we did a calculation at 500 ohms, but now what's that total noise look like from 10 ohms, 100 ohms, and we have up to 100 kiloohms. The dotted line here is showing the total noise in nanovolts RMS, and it's just interesting to see how it goes up with resistance. Then the bar chart here is showing the contributions of noise for measure, source, and Johnson. And this is in terms of voltage noise density. And this is also interesting to see how as you go up in resistance, right, you really don't see much source noise at these lower resistances. Only at 100 kiloohms you start to see some, but your Johnson noise becomes prevalent. So that's something to consider, right? What's the resistance of your sample you're measuring? If you're at a really high resistance, the having a really good measure and source noise spec probably isn't as important because you're going to be dominated by Johnson noise. Whereas if you're in the lower resistance regions, then the measure noise is what's most important here. This chart here is now showing still the total calculated noise, nanovolts RMS, but now we're going to compare to two other lock-ins, the SR860 from Stanford Research and the MFLI from Zurich. Both of them have a voltage measure noise, 1 kilohertz of 2.5 nanovolts per square root hertz. The SR860 doesn't have a source reference noise spec. I would assume it's maybe because it's not so good, but at the same time, as we previously saw, the source noise isn't as important. It has a pretty low contribution if you have a shunt resistor, right? You're not using it as purely a voltage source. Then the MFLI, they spec at 43 nanovolts per square root hertz. So this is just a chart you could go back, take a look at. It's kind of interesting to see. Once again, we go up in resistance, what the different total calculated noise is. Now we're looking at the same chart as we did before with the M81, but instead of 1 kilohertz, we're looking at 10 hertz, right? So we're looking at that lower frequency now. And just in general, kind of a nice comparison here of how does the noise look over varying resistances. You can go back and take a look at this. We'll go ahead to the next slide already. Once again, we're looking at a comparison of the M81 with the SR860 and MFLI, but now at 10 hertz, right, that lower frequency. The M81, the voltage measure noise is 5.5 nanovolts per square root hertz. The SR860 is at 10 and the MFLI is at 7. So as you can see, the M81 really excels at that low frequency measure noise. And It's great comparison here showing the total calculated noise. You can take a look later through these values. And it's just interesting to see as your resistance increases what that looks like. Already at 100 kiloohms, the M81's noise is 21, right? We're looking at noise in terms of nanovolts RMS, where the SR860 and the MFLI is at around 40 nanovolts RMS here. And something that's interesting is I'll show a quick graph here, which is nice, of the M81 compared to two different other lock-ins. We're not going to specify who. And we plotted the voltage noise density. The M81 is the blue line here. And the other two lock-ins, right, we have that in red and in gray here. You can see the M81 is very straight actually for the whole frequency spectrum. Of course, it goes up at the lower frequencies, but it's relatively uniform, where the other two definitely have a higher lower frequency noise and then they tailor down. So next we're going to look at a comparison of the 10 hertz and 1 kilohertz and start to talk about, all right, if the noise is typically better, or yeah, it is better at 1 kilohertz, even if it's minor in terms of the M81, why would you run at a lower frequency? And people typically end up having to run at a lower frequency. And so let's look at a comparison. Real quick, here's a comparison of the same charts we've already seen of 10 hertz and 1 kilohertz. Take a look at this later on your own time. Just an interesting comparison. As I just said, your noise at 1 kilohertz is going to be less. For the M81, it's really not that huge of a difference, but when you look at the SR860 and the MFLI, there's definitely a larger difference between the 10 hertz and the 1 kilohertz noise. So let's get into why would you need to run at 10 hertz. A big reason for that is capacitance. Your cabling has capacitance, and you can think of the cable capacitance as a capacitor in parallel to your device. As the frequency increases, the impedance of the capacitor decreases, which means more current is flowing through your capacitor instead of your device, and this results in a higher error in accuracy. This is plotting the device resistance over a frequency of 10 hertz, 100, and 1 kilohertz, and looking at what's the equivalent device resistance error from having a cable capacitance of 1 nanofarad. 1 nanofarad is a standard cable capacitance value we've seen in our own setups. And there's some online calculators you can use to estimate what's the cable capacitance that you could likely have in your setup. And the equivalent device resistance error, that's comparing the true device resistance, comparing that to once you have that capacitor in parallel, that new R equivalent resistance, like what's that error? And you can see at 10 hertz, it's a very low error. You can hardly see it on the chart. You go to 100 hertz, gets a bit higher. 1 kilohertz, right? It's really quite significant. At 100 kiloohms, you're seeing close to 40% error there. And there are things you can do to compensate for this, to calculate out this capacitance effects, but you can only do this up to a certain range, right? When you're seeing 40% errors, you can't calculate that out. You're going to be having some issues in your accuracy. The M81 actually has a really cool feature where you can select it to automatically calculate out the capacitance effects. And that's a really nice, neat, unique feature. It just makes things easier so you don't have to worry about it. But that too has its limitations. You can only compensate up to a certain point. And that's why a lot of people then have to run at a lower frequency. They have to start running in this 10 hertz range because they just have too much capacitance effects and errors from that. Bring it all together, looking at those same charts of 10 hertz and 1 kilohertz. We're plotting the noise as we've seen before. This black dotted line here is the equivalent resistance error from using 1 nanofarad of cable capacitance. You can see at 10 hertz, it's really low. It's really hardly affecting your measurement. But then when you go up to 1 kilohertz, it's pretty substantial, especially when your resistance starts to increase. So if you have a higher resistance, you're very likely going to have to run at a lower frequency. And finally, there's also effects from crosstalk. Crosstalk is signal interference between your cabling. So we have seen crosstalk effects in our setups of around 30 nanovolts and at 1 kilohertz. But if you go down to 10 hertz, that crosstalk goes down to 0.3 nanovolts. And if you're trying to measure a signal that's in the nanovolt range, right, you're going to have a lot of trouble if your crosstalk is at 30 nanovolts. So you'll want to run at 10 hertz where it's a lot lower. And this is why it's important to know, what's your cable capacitance? Do you need to run at a lower frequency? Because if you do, you need to be looking at the 10 hertz noise specification instead of the 1 kilohertz noise spec. We talked a lot about noise. Now let's touch on accuracy. Accuracy, right, it's pretty straightforward, but something that's often forgotten is the tempo, which that will add additional accuracy error to your measurement. Below here, I pulled the accuracy specs for the 10 millivolt range for the M81, SR860, MFLI. The M81 has really good tempo. We have a tempo gain of 0.0006% with a 1 microvolt offset. The SR860 actually doesn't specify any tempo, and the MFLI has a 0.1% tempo gain. And they don't specify an offset, but I'm assuming they just contribute that into their gain. So in this example, let's say there is a 5C temperature change, and we have a perfect reading of 10 millivolts. What would that reading be, including the error from accuracy and the tempo error? For the M81, our error specification is very good, so you actually don't even see it. It's only the tempo drift here, and you'd have a reading of 10.006 millivolts. Going to the SR860, the accuracy error is higher, and you'd have a reading of 10.1 millivolts. And this is all assuming worst case, right? We're looking at the worst case error accuracy spec and tempo. So you have 10.1, but you don't know what the tempo gain is. You have no idea how much your reading is going to fluctuate with temperature changes. So that could be concerning to you if accuracy is a critical specification. Then for the MFLI, it has a bit higher of an accuracy error. And with the tempo, you get a reading of 10.25 millivolts. So I thought that was just kind of a cool way to see how the temperature and accuracy would affect a reading. If you're taking a measurement that's going overnight, you could easily have a couple degrees of a temperature change. And if you don't have a good tempo, that could mess up your result. Or let's say you're in a lab and the temperature is always changing, right? In the summer, it's so hot. And then in the winter time, it's really cold. You won't have very repeatable measurements if you don't have a good tempo. So just something to keep in mind. If accuracy is important to you, look at the tempo. A feature that's often overlooked is having a fully differential setup for your lock-in measurement. Most lock-ins have a differential measurement, but their internal source is single-ended. If you wanted a fully differential setup, you would need to get an external source that's differential, or the M81, the source is differential. And so you'd have a fully differential setup with the our source and measure modules. And a reason for having a fully differential setup is it's a lot less susceptible to EMI. This data here is really cool in showing the effects of that. We have in the black Lakeshore M81, and then the red and green are two different lock-ins. And they have a differential measurement, but their source is single-ended. you can see how it's really a lot more over the place compared to the M81. And so just keep in mind, if you're trying to have your measurement be not susceptible to EMI, you'll want a fully differential setup. To summarize, to put it all together, when selecting a lock-in, you need to first make sure that the max bandwidth of the lock-in is large enough for the signal you're measuring. After that, what's the noise floor of your lock-in? Do you need to be more concerned about the 1 kilohertz spec or the 10 hertz spec? And as we talked about cable capacitance, crosstalk, this all affects what region you should be running in. Then what are the accuracy specifications? If accuracy is important to you, then what's the temp code? Do you want to source current? Most lock-ins have an internal voltage source, and if you want a current source, then you'll likely need an external current source. The M81, you could have a current source module or a voltage source or both. Then what's the input impedance requirements for your experiment? Your sample, its impedance has to be a lot lower than the input impedance of your lock-in. Do you want a fully differential setup? As we talked about, a fully differential setup means your experiment will be less susceptible to EMI. How important is easy use? The M81 was designed to be really easy to use, where a lot of traditional lock-ins are actually quite complicated and have a long learning curve on how to use them. The M81 was designed to be as simple as possible. And yeah. And finally, do you want to minimize cable length? If you want very short cables to your sample, you'll likely need a preamplifier with your lock-in. The M81, the modules kind of act like preamplifiers, and they can already go very close to your sample if you're trying to minimize cable length. And finally here, I have this chart showing comparison of the digital lock-ins, looking at the key specifications. I'm not going to go through any of this. It's yours as a reference. So thank you very much for listening.